Hello everybody, this is Dimitris Stamatellos, and in this video I will go over the Exoplanets project. Just to give you an idea of what it is expected from you to do, and maybe explain a few things that may not be clear in the GitHub file. So let me share my screen first of all. Okay. So the Exoplanets project, it has 4 sub projects, and starting from the first one, we're gonna talk a little bit about Keplers laws. So in this one, especially, you will learn how to use Kepler's third law to connect the distance of a planet from its host star and the period of the planet. So initially here, what I do is just have all 3 laws just for completeness. So the first law states that the orbit of every planet is an ellipse with the sun at one of the 2 foci. The second law, that a line joining a planet and the sun sweeps out equal areas during equal times intervals. Basically, that means when the planet is farther away from the star, it moves slower, whereas when the planet is a bit closer to the star, because the orbit is elliptical, then it moves a bit faster. And the third law that we're gonna focus on this exercise states that the ratio of the square of an object's orbital period with a cube of the semi-major axis of its orbit is the same of all objects orbiting the same primary. And the equation that gives kind of describes the third law, it's this one that you have here. Maybe I can make. Okay, I can make it a bit bigger. So in this equation, P is the period of the planet, and A is the distance, the semi-major axis, which is for a circular orbit, is the distance of the planet from the star. Here M is the mass of the star, and G is the constant of gravity. So you can make this equation a bit more simple by applying it for the Earth. Okay, so the Earth moves around the sun. So I put in, for the mass of the star at the denominator here, the mass of the sun. So this is denoted by this little symbol down here. And this symbol up here for the period and the semi-major axis corresponds to the Earth. Okay, so this is the general equation up here, and this equation down here is the equation for the Earth. Then what I do here is just I divide those 2 equations, and I get this equation here, which effectively, by doing this division, what happens is that all the constants just go away. So we know that for the Earth, the semi-major axis is 1 AU, that's the astronomical unit, and the period is 1 year. So if in this expression we use the period in years and the semi-major axis in units of AU, then we get this very simple equation. So you need to remember, it's important that in this equation you don't use the International Systems Unit. We just use years for the period and astronomical units for the semi-major axis. And for this sub-project, we have 2 tasks and 1 question. These are optional. I realize that maybe all these tasks take a lot of time. So I made some of those optional, so you don't have to do it. If you have time, you can do them. But the more important ones, maybe the bit more challenging ones, are the ones that are required to do. And again, you don't have to do everything, just do as much as you can. Don't worry too much about it. Just need to put an effort in it and just try to do your best. So for that first task, we need to define a function that returns the distance of the planet from its host star, from its period P, and the mass F of the star. Effectively, we just have to define a function that uses, basically we need a function that returns uses this equation to return the period, to return the distance from the period and the mass of the star. Okay, and I give you some hints here that you need to import some packages like numpy and matplotlib.pyplot. That's for plotting stuff. Actually, that's for plotting stuff, so that's for the next one. And then for the second task, task 1b, you will use this function that you defined before to plot the semi-major axis of planets with orbital period between 1 day and 5 years for stars between 0.1 and 2 times the mass of the Sun. Okay, so for each, so here I say that you need to use 5 values between 0.1 and 0.2. So let's say for a Sun-like star, so a star with a mass of 1 solar mass, you need to plot the period of the planet versus distance. Okay, so orbital period on the x-axis and distance on the y-axis. And you will do that for 5 stellar masses. So also you can need to plot it for 0.1 solar masses and then up to 2 solar masses. You can choose 5 values. So basically you will make a table or some kind of array that has 5 different values for the mass of the star. And then you can use this graph to answer this question that relates to the observability of planets, of exoplanets for space missions. Yeah, so these all are optional. Effectively, what you need to do is use this equation to make a function, a Python function, and then plot this function for different, basically plot the relation between period and semi-major axis for different stellar masses. And one interesting thing that you need to note in this equation is that the period of the planet does not depend on its mass. It depends on the mass of the star, but not on the mass of the planet. Okay, so that's the Exoplanets 1 sub-project. For the second, we're going to plot the habitable zone around the star. So if you watch the video, the lecture, Exoplanets lecture, I talked about the habitable zone. So that's basically the area around the star where liquid water can exist. So liquid water can exist between 0 and 100 degrees Celsius, or equivalently between 273 and 473 degrees Kelvin. So the distance the temperature of a planet, okay, depends on many factors, but one of the factors that determine the temperature of the planet is its distance from the star. So here I've done a kind of small calculation of the temperature of a planet. I mean, you can look over the calculation. You don't, maybe you can understand it, but if you don't understand, don't worry about it. But you need to understand the final equation that I have here. So in order to calculate the temperature of the planet, what I do is assume that the planet is in equilibrium. That means that it receives the same amount of energy that radiates away. the amount of energy that the planet receives comes from the star. And then because the planet is hot, it radiates some energy. And by balancing these two energies, we can calculate the temperature of the planet that is given by this equation here, where this capital A is the albedo of the planet, which determines what fraction of the incident radiation is reflected. So A equals 1 means that all the radiation is reflected. It's basically the planet is like a mirror, which of course this is not the case. Whereas 0.7 means that 30% of the incident radiation is absorbed. And then by solving this equation for the distance A, we can relate the distance of the planet and its temperature. So remember at the beginning I said that the temperature for liquid water needs to exist. It needs to be between 273 and 373 K, which means, and if we put this value here, I can get a minimum distance, the minimum distance that the planet can be close to each star. That is, the maximum distance that the planet can be away from the star that cannot be too cold. And by putting 373, we get the minimum distance that the planet can be close to the star so that it won't be too hot for liquid water to exist. So for this second task, what I have asked you here to do is to make a graph of the mass of the star in solar masses against the inner radius and the outer radius of the habitable zone. Okay, and actually maybe I can give you a hint of how it kind of looks like, so you know what to aim for. Okay, let me stop sharing this screen, and now I'm going to share a different screen. Okay, so here what you have, I plotted two lines. The red one shows the inner boundary of the habitable zone. So what I did is I fixed the temperature in that equation, and then what I varied is the distance from the star and the stellar mass. Okay, so the higher the stellar mass, the farther away the planet needs to be from the star. Okay, so that's the inner boundary and that's the outer boundary. So for a habitable planet to exist, it needs to be in between those two lines. Okay. Now going back to my previous. Okay, so I give you instruction how to construct this graph, and also you need to label your axis, put your title and legends for the different lines plotted, so you can make your graph a little bit nicer, look nicer, a bit prettier. And then you can plot also a point with the Earth on it. And okay, if you just looked at the graph that I just saw you, you saw that the Earth was outside the habitable zone, which of course is not the case. Maybe so you can do maybe a little bit of search on the internet to explain why this is the case, what we have missed in this simple calculation. Okay, so now going to the transit modeling, which is parts 3 and parts 4 of this project. So in part 3, I just give you some background information about transits. I discussed a little bit about this background information at my lecture. So here you have a transit when the planet passes in front of the star and gives you this characteristic dip in the brightness of the star. And from the properties of these transits, you can get information about the planet. So here I just have some, I think they are from real data. So you have this kind of transit, you have a planet that gives these 3 transits here. So every time the planet passes in front of the star, you will see this dip in the relative brightness of the star. So this is one is a flux of the brightness of the planet when there's the brightness of the star when the planet is not in front of it, and then it drops to 0.993 here when the planet passes in front of the star. Just a note here, I noticed at some points I use the word flux, but you can think about that it's exactly the same word as brightness of the star. Okay, so you see it's the same planet, so the transit dip, the transit curve is exactly the same at its time. So here it's plotted brightness versus time. So by measuring, let's say, the time that this minimum occurs and this minimum occurs, you can get the orbital period of the planet, how often it passes in front of the star. And then you can use again the transit curve to find the radius of the planet. So there is this relation that you can use. So the bigger the planet, the bigger the depth of the transit. And this is the equation that you can use. And here what I've done is just I use this astronomy module. It's called pyastronomy.model suite. Sometimes it's a bit tricky to install it. If you have any problems installing this module, this package, just ask some question on Slack for us to help you. And this one, what it does, it's a mathematical model that we can put the properties of the planet and give you the transit. Okay, so you can see I have different parameters. For example, the planet orbital period, that is given in days. So when I define, when I use this command here, what I do is I use this function that from the package pyastronomy, and I create this object here that's called a planet. So a planet is an object that has information that includes inside all the properties of the planet. So here I set the period of the planet with this command, with this line. Here the orientation of the planet, where the planet passes exactly at the middle of the star, a bit higher, a bit lower. Here the semi-major axis of the planetary orbit, the time offset of the transit center, basically that tells me when the transit happens, and the radius ratio between planet and star. Okay, so here there are also some other parameters that are a bit more complicated, so I won't explain them, so you don't have to change those. Okay, so if you just run this program that I have here, right, then you produce your own transit curve. Okay, then what I will do is I can just change the parameters. Okay, you can see here the bottom here is at 0.988. So what I'm going to do now is just, let's say, what shall I do? Let's just increase the radius ratio between planet and star. So I just make my planet a bit bigger in size. Let's put it 0.5, which is quite large. Okay, just see this one, 0.988. So now I'm running it with a new parameter. See that the shape of the transit has changed a little bit, and also it's gone down to 0.7. And here I plot it up to 8 days, so I see only one transit. So you can see the period of the transit is 6 days. So what can I do is I can increase a little bit the scale on the x-axis, on the time axis. Okay, so I can, instead of going up to 8, I can go up to, let's say, 20 days. And then you can see more than one transit. Okay, so what here again, these two tasks are optional, but I think it's a good way for you to change parameters and just play with this function just to see how transits look for different planetary systems. So here I ask you to change the size of the planet and see, compare the previous and compare the two planets, how different are the transits. And the second is to change the semi-major axis of the planet, just again to see what happens. Okay, so that's part 3. I'm going now to part 4, which probably is the most interesting part. So in the previous 3 parts, you're just basically building up your knowledge to understand things a little bit better. So now you're going to apply this knowledge in actually discovering planets in real data from the Kepler space mission. If you look at the GitHub on the Exoplanets directory, you'll see that there are these files that are called txt. They have a name here. The name is refers to the name of the star. It's a kind of a very long name. So what you will do, you will import this data. This data have information about the relative flux, the relative brightness of its star with time. Because it's a bit strange file, I have here what can you use? You can use to import the data and the modules that are needed. And then after I read the data, I convert them to NumPy arrays with this by doing these things here. So let me run this one. Okay, and I also just sometimes when you do programming in Python, you just do some print commands just to output some stuff just to make sure that everything works all right. So now I have imported this data here. And then what I can do, what I ask you for the first arc is to let me see. To plot the data, first of all, yeah, you need to plot the data. That's the easiest thing. Okay, and I ask you first to do it in hours because it is a bit it's a bit easier, I think, for the tasks that come afterwards. So when you read this, the time is in days, so you need to convert it into hours. So let's just do this first. Just have a new box here. Okay, and then I'm just gonna plot it just to see a little bit how they look. Okay, so it looks something like that. Of course, you can put your titles here and make it nice, and axis labels and so on. Okay, so here you have this. Okay, this one we don't look at the transit that we had before, but you need to think that this is a kind of a very wide range of times. So it's good in order to see what's happened. It's good to zoom in at a part of a graph. So what I'm going to do here is I'm going to change the limit of time. Let's say 51600 hours. So that's that gives you the hours after a specific time that is given at the beginning of the file. So you can get more information if you read the instructions that I have there. Okay, so this is time. Let's say I'm going to plot it up to 52,000 hours. I've done something wrong. Yes. Okay. I think maybe again I did something wrong. Let's go back. The thing is, every time that I execute it, I change the time, so that's not good. Let me import it again. And what I'm gonna do is just change the time in the previous box, because now every time I run in the box, the time changes again and again, but I just want to change it just one time. Okay, so you get a bit of kind of a tutorial of how to make mistakes and how to correct those mistakes. Okay, let's run the first box. Okay, and then let's do the second box. And also just change the, before doing that, let's just change the limit in X. Let's say 1, let's say 300 up to 52 hours. Okay, hopefully now it should work. Yes, and it worked. Okay, let me increase a little bit the X-axis, so the limit, just to bring this in the center. Okay, here you notice, okay, you can just barely see them, but there is kind of a transit here. It goes down and it comes up. So this is one planet. And then you can, if you're a bit careful, you can see a second transit here, second planet. So it's a smaller transit and a smaller transit here. Okay, again, we can zoom in a little bit. Let's focus first on the big planets. So the bigger when you have this big transit here. Let's 51, 750, let's see. Okay, I think I put one more. Okay, you have to be a bit careful. Okay, so now the more you zoom, the better you can see the transit here. All right, let's zoom a bit more. You see now the transit is more visible. And if you look, there's a kind of, probably there's another planet, 1, 2, see this little thing here. But anyway, here it's easier to find the properties of this planet, and this one is quite hard to distinguish it. So we'll just focus on this planet, and also you can focus in the second planet that's here. Let's zoom out again a little bit. Zoom out more. Let's go up to here. Okay, now I have everything again. So now I want to focus on the second planet. So let's go up to 52,000, let's say. And now, because I want to see what happens for this small planet, I need to change the y-axis. Scale 2. So say 0.997 up to 1. So now you can see the second planet a bit better. It's this one and this one. Okay, so there are at least two, maybe there's a third planet in this system. So what you need to do for this task is to actually calculate the properties of the planets. You need to calculate the depth of the transit, and you calculate the period of the transit. So the time from this minimum to this minimum. And if I zoom out a little bit again, you will notice that the brightness of the star changes during this time of observation. So it starts at 1 here, but then it goes down a little bit and then starts going up again. So when you calculate the depth of the transit, you have to also find, okay, you don't subtract it. Let's say if this is 0.99, that's not the real depth, that's the kind of what you see here, but so you need to take into account that the luminosity of the star, the brightness of the star is not 1 here. So you need to find what is the luminosity of the star before and after the transit, and then find the depth of the transit. Okay, so what I ask you to do is to, well, the first task is to import the data. So I gave you an idea how to do that. The second task is to identify how many planets there are in the system. And the third task is to choose two transits for one planet. First of all, get the bigger transit, so the bigger planet, and then follow the steps to calculate the radius of the planet and its period. Okay, and then what you can do, take the extra step and just try to see whether these planets are in the habitable zone. Okay, and here I give you the mass of the star and its radius. So you need its radius to actually calculate the radius of the planet. And then you can calculate whether this planet and the habitable zone, but just plot them in the graph from the second task. Okay, so you can do it for more systems. I have more files of observations from Kepler there, but I think probably this will take you quite a lot of time. So don't. Okay, I mean, if you're interested, you can do it, but it's not really required. And then after you calculate the properties of the planet, you can also go to some of these catalogs, find the planet, and see whether the values that you calculate are near the correct values. And you have to be careful here that, okay, there are stars sometimes have different names. So here I give you the epic name, and here I give you the Kepler name. So K2-23, it's the same star as epic, all this kind of big number. Okay, so probably you're a bit confused now, but I think once you kind of go step to step through these tasks, I think it will be clearer. And of course, don't forget to ask questions. That's why I have the Slack channels. So they're going to be two helpers that can help you, give you some advice, answer your questions in Thai. But also, I think it's good for you to try to explain yourselves in English. So there are also two PhD students here in the UK that will be answering your questions in English. So I think what you should try is just have at least one question in English, so you can come in contact with our students here too. Okay, I know maybe it's a lot, but I say, I mean, if try to do as much as you can. Don't worry if you cannot finish everything. Just choose the most interesting stuff to do. Okay, that's all for now. Hope you enjoyed the video, and I'm looking forward to receiving your questions. Bye now.